Welcome to Study Loop.
This is chapter 21, problem number 52. We are given this figure 21-37 on your textbook, and we are asked to determine delta I over delta T rate of change of current at T equals 0 when the battery is connected. So the switch is in this position, not the other position that is represented by the dashed line, for the LR circuit of figure 21-37, and show that if the current continued to increase at this rate, we're going to find this rate, and then if it continued to increase at this rate, it would reach its maximum value in one time constant. So then at the end of it, we need to calculate that time constant. So the first thing is first. So when that moment when the battery is attached to the circuit, RL circuit, the inductor prevents the current from flowing. So at T equals 0, actually the current equals 0. So if the inductor prevents the current from flowing, which means there is no current flowing across this resistor initially, then there is no potential drop that is given by I times R, right? So for the resistor, the potential across the resistor, let's call it V sub R, is going to be 0 initially. So all the battery's potential is going to be the potential across the inductor, right? So then, when that's the case, remember this equals to L times delta I over delta T, right? The inductance times the rate of change of current with respect to time. So since we know now that the potential drop across the resistor is 0, then the battery's potential equals to the potential across the inductor. Then we can rewrite this equation as VB equals L delta I over delta T. Let's get an expression for delta I over delta T since that's what we are asked. Delta I over delta T then is going to be equal to the potential across the battery divided by the inductance initially, right? So this is important, the entire equation. We're going to use this later on. So now, what happens when I max is reached, right? How is that going to happen? That's going to happen when the potential across the inductor now is 0 and the entire battery's potential, well, in the figure it's V naught, but I use VB. Let me just put it here that they're the same thing. So then the entire battery's potential is going to be observed across the resistor. So then from Ohm's law, it's going to be equal to I max. This is when the current is maximum times the resistance, right? So then I max from here, then if we divide both sides by R, is going to be the potential across the battery divided by the resistance, right? This is another equation that we're going to use. Now, we are asked to calculate the time interval that it takes for the current to go from its initial value at this rate to the maximum value. Then how are we going to set up that equation? Is I max then is going to be equal to the initial value, which is I naught, times at this rate, right? Delta over delta T times the elapsed time. So the time that it takes for the current to reach that I maximum, right? So then that's the elapsed time is what we want to figure out. So then if we try and isolate that out of this equation, I max minus I naught is going to be equal to delta I over delta T times T prime, right? If we divide both sides by delta I over delta T, then we have delta T over delta I max minus I naught equals the elapsed time. So let's remember what we found I max to be from the first page. I max was the potential across the battery divided by the resistance, V over R. And I naught, remember we said that it was 0. And this ratio, delta I over delta T, we found out that it was the potential across the battery divided by the inductance. Potential across the battery divided by the inductance. Then if we take the inverse of this, delta T over delta I, then it's going to be L over VB, right? So we're just going to plug everything in this equation. Then L over V sub B equals to I max VB over R minus 0. So then L over VB times VB over R. For elapsed time, we have the inductance divided by the resistance.